Calculus on day 7, we're going to be looking at composite functions, which is where you have a function within a function. So we have used those in grade 11 and grade 12, and I'm just going to remind you of what those would be. So if I have two functions, one is f at x and one is g at x, I can write a function as g of f at x or g at f at x. It just starts to sound like a mouthful. But what this means is my important function or outside function is g of x. And g of x says multiply 2 by whatever your x is. In this case, I am multiplying f at x instead of x. So g says multiply something by 2. And f at x is x cubed. So I'm going to do 2 times x cubed. Whereas f at g at x says my function f, which is my primary function, is to cube something. So I am going to take whatever's in the brackets, g of x, and I'm going to cube it. G of x is 2x. And I'm going to cube that. I'm going to get 8x cubed. We don't get to the same place if we have g of f at x or f at g at x because we have different primary functions. Another way to write this, which is different notation, the same thing would be g composed of f at x. And we would say gof, g composed of f at x, and we pronounce it as gof. Okay, let's do just a couple more. If f at x equals root x and g of x equals x plus 5, determine fog. So f composed of g of x is the same as f at g at x. So if you have a preferred notation, either will do. I like the function notation a little bit better than gof and fog, but anyways, f at g of x means f is your primary function, which is square rooting something. G of x is x plus 5. So I have the square root of g of x. Whereas gof is take something and add 5 to it. So that would be root of x plus 5. Again, we get to a different place depending on which one is the primary function. Let's just look at the domain for a second. F at x equals root x. Our domain would be x greater than or equal to 0. G of x would be x can be any real number. However, the domain for fog, or f at g of x, would be x greater than or equal to 0. And in this particular case, its picture would look like square root of x moved 5 to the left. But since we had a restriction that x had to be greater than or equal to 0 at some point along the journey, then our domain would remain x is greater than or equal to 0. X is greater than or equal to 0 would be the domain for this thing as well. So we would write it as XER, x greater than or equal to 0. So when you get to class, we are going to ask you to practice just with composite functions before you start to worry about the chain rule. So I'm going to just leave a note of that and let you pause your brain for a minute. And we're going to continue and talk about the chain rule. For the following function, we have h at x equals the cubed root of x over 1 minus 2x. You see it and you just about cry because it's just so ugly. So we are going to do the skills that we've already used to find the derivative. I'm just going to write this function out in a way that might make a little more sense for the power rule. I have x over 1 subtract 2x raised to the 1/3 power. So that we have a tool for. We know our power rule. Our derivative would be bring down the power, 1/3. Sorry, bring down the exponent, reduce the exponent by 1, which would be negative 2/3. Okay, and I'm going to write the inside I brought the exponent down, reduced it by 1. Don't forget the guts. Okay, the guts of that thing. Oh man, it's a quotient. So I've got to use a quotient rule for the guts of that thing. Okay. So for my quotient rule, I have the derivative of the top, or first, times the bottom. Subtract the first derivative of the second, which is -2, all over the second or bottom squared. Just taking a second to check. Check the first derivative of the second. I think I'm good to go. So that is my derivative. If I'm looking for the derivative at a certain place, then I would substitute that value in right now rather than do any tidy up. But it doesn't say so, so I'll see if I can tidy it a little bit. I am going to leave that 1/3 and ugly bracket. I'm just going to see if I can tidy up the square bracket a little bit. I have 1 subtract 2x plus 2x. So I end up with a 1. That's kind of nice. 1 minus 2x squared. I think it wouldn't be all that helpful to do anything more. Okay, let's introduce the chain rule. So if you have a function within a function, our composite functions that we were talking about before, then our derivative is, take the derivative of the outside bit, don't forget the guts. There is a second way to look at it, is where we use Leibniz notation. And if you have a function y equals and u equals, we can write dy dx equals dy du du dx. Let's try it again. The method that we used at the beginning was basically the chain rule in its first form. We're going to try it with the second form. So I'm going to rewrite my function as, wow, that's ugly. I have ugly under the root sign, so I'm going to call the ugly u. U equals x over 1 minus 2x. And my function is really u to the 1/3. So all I've done is said it's too much to handle. I'm going to separate the bits. My derivative is, if I want the derivative with respect to x, my chain rule would be dy dx equals dy du times du dx. You can see that it looks like a chain. It looks like du and du would cancel each other out. It's not exactly the way it works. But this is my chain rule, written with Leibniz notation, and here we go. Dy du. I'm taking the derivative of this guy with respect to u. Well, that's pretty easy. I bring down my 1/3. I reduce the exponent by 1. Done. Du dx. I'm taking the derivative of this guy with respect to x. Oh, that's a quotient rule. I know how to do that. It would be the derivative of the top times the bottom, subtract the top derivative of the bottom, all over the bottom squared. So no panic attacks for this one. It's just straightforward. But I now have a derivative that has 2 letters of the alphabet in it, and that's not entirely helpful. So all I'm going to do is replace my u with what it is equal to in terms of x. So I have 1/3. I'm going to replace him with what he's equal to, which is x over 1 minus 2x. I'm going to tidy this thing up. I've got 1 subtract 2x plus 2x. I've got 1 over 1 subtract 2x squared. I've gotten to the very same place as I did with the last one, and the mental confusion was just a little less. If I had the function y equals 3 times x squared minus 1 squared, subtract 5 times x squared minus 1 plus 2. I don't know why you would, but if you did, you can say, oh man, that is just too much work. But I could replace x squared minus 1 and call it u. So that really I have a function that's much more simple. I have 3u squared subtract 5u plus 2. And that's easy to deal with. So if I want my derivative in terms of x, I want dy dx, I can use the chain rule, which would be dy du, du dx. Okay, so dy du is not hard at all. I bring down the exponent, that becomes 6u, subtract 5. That's dy du, and I'm going to multiply that by du dx. The derivative of u with respect to x is just 2x. Fantastic. So I don't like it that there's a u in here and an x, so that gets a little bit confusing. I'm going to replace that u with x squared minus 1 and multiply that by 2x. No mental strain. I've got the derivative of something quite ugly. X squared minus 6 subtract 5 times 2x. I seem to be taking the long road here. 12x cubed subtract 22x. Okay, if we had functions set out for us as y equals 2u cubed plus 3u squared, and u is x plus x to the 1/2, and I'm asked to find the derivative of y with respect to x. I know that my letters don't match, but I know I can use the chain rule. I know dy du and du dx can get me to dy dx. So I have, oh, and I want to know this when x equals 1. Here we go. dy du is nice power rule 6u squared plus 6u times du dx. So I'm taking the derivative of u with respect to x. It would be 1 plus x to the 1/2 is, bring down the 1/2, reduce the exponent by 1. Awesome. I want to know the value of this thing when x equals 1. The laziest way to do that is to say, all right, when x equals 1, what is the value of u? So u equals 1 plus 1 to the 1/2, which is the square root of 1, which is 2. So when x equals 1, u equals 2. So our derivative, dy dx, when x equals 1, is 6 times 2 squared plus 6 times 2 times 1 plus 1/2 times 1 to the negative 1/2, comma, when x equals 1. Far easier than doing a whole generalization and cleanup. We just substitute the value as soon as it's humanly possible. So we have 24 plus 12 times square root of 1. 1 plus 1/2 is 3/2. 36 times 3/2 is 18 times 3, which is 54. You might want to check that on a calculator. Okay, next example. Okay, we have y equals 2u cubed plus 3u squared. Sorry, did them out of order. Let's do this one, which is actually b, wasn't it? I apologize for that. Y equals u cubed, subtract 5, u cubed minus 7u squared, where u equals root x. So for the record, the original function before somebody kindly separated it for us was y equals root x cubed, subtract 5 times root x cubed, subtract 7 root x squared. That's really, really, really ugly. So somebody said, okay, I see root x's everywhere. Let's make u equal to root x. And then we'll have a little bit nicer function to deal with. not overly, but a little. So if we want to find our derivative with respect to x, and we are asked when x equals 4 to find the derivative for that, we'll worry about that later, I know I can use the chain rule. dy du, du dx. All right, so dy du. I take the derivative of y with respect to the letter u. I have the power rule, 3u squared. Subtract. Now I have a power rule. I bring down the 2, reduce that power by 1. Don't forget the guts. So the guts of the inside of that bracket is 3u squared, subtract 7, times du dx. du dx is the square root of x, which is the same as x to the 1/2. The derivative of that thing is 1/2. Reduce the power by 1. Done. Okay, that is the derivative. It's hideous beyond all reason. But I know I want to find this derivative when x equals 4. So I can put a 4 in for x. That would be lovely. But it would be really nice if I knew my u value at that time so I don't have to tidy this whole thing up. Well, I can do that. If u is the square root of x, oops, then when x is 4, square root of 4 is 2. So when x is 4, u is 2. And now I can substitute those values in and save myself a lot of work. So I have 3 times 2 squared. Take away 10 times 2 cubed, minus 7 times 2, times, wow, it's ugly. Subtract 7, all of that, times, when x is 4, I've got 1/2 root of 4. So I'm just trying to make that a little bit nicer so I don't make too many mathematical errors. Here we go. 12, subtract 10 times 8, subtract 14 is -6, times 12, subtract 7 is 5. All of that. I should have put that all in brackets. I think, just for sake of clarity, that times 1/2 times 2 is 1/4. Okay. 12 plus 60 times 5. Okay, 312 fourths, which simplifies to 78. And the last one before your head implodes, we are going to do the other function notation. So y equals g of h of x, where h of x equals blah, blah, blah. And I give you bits and pieces of information, but not the whole thing. So if we are asked to find dy dx when x equals 3, and I have a function within a function, I need to use the chain rule. Okay. There are 2 versions. The one version that we're going to look at now is, okay, I take the derivative of the primary function, and don't forget the guts. So I don't really know what g does, but I do know that I want the primary function's derivative of x squared over x plus 2. And I want to multiply it by the derivative of the guts. Well, that I can find. The derivative of the guts is a quotient rule. So I have the derivative of the top times the bottom. Subtract the top derivative of the bottom, which is just a 1, but I thought about it, over the bottom squared. Okay. I want to know this thing when x equals 3. So instead of agonizing about the fact that I don't actually know what g does, I'm going to put 3 into this thing. So g prime of Okay, 3 squared is 9 over 3 plus 2 is 5 times. Okay, I have 6 times 5, subtract 9 over 5 squared. I'm just substituting in and doing the, oh my goodness, look at that. I want to find the value of g prime of 9/5. Well, they just happen to give me that. I know that that is -2 times. This is 30, subtract 9 is 21 over 25. So my final answer would be -42 over 25. Strange, but true. There are a few questions like that in the textbook, so I wanted to make sure you saw at least one.